Hello everyone, I'm Alexandre Blain, second year PhD student at INRIA in Paris. And today I present to you Notip, which stands for Non-parametric True Discovery Proportion control for brain imaging, as part of the 2023 OHBM educational course on beyond Blobology. And so this is originally a paper we published in Neuroimaging with Bertrand Thirion and Pierre Neuvier. So, of course, we're interested in the problem of brain mapping, which is that we are trying to associate different cognitive functions to relevant brain regions. And so you have an example, a few examples of contrasts on the slide here, and relevant regions that are associated with it. So from a more concrete standpoint, how do you build such a mapping? So the idea is that you will have this sort of input at your disposal. So you have 16 subjects here that are performing a certain task. And actually what you're trying to solve here is a multiple testing problem, in the sense that you want to test for each voxel that's present in the brain, whether it is active or not for the contrast that you're interested in. And so the first thing that you will do tackle this multiple testing problem is to simply perform, let's say, one sample t-test across all of those samples. So this is how you obtain a single statistical map, which is on the screen now. And so this is basically the object that users will perform inference on. And so the first step to retain regions that are relevant with regards to the control that you're looking at is to perform some sort of thresholding. So this is what we do here. And you see that we extract some sort of relevant regions for the control that we are interested in. So that being said, we now want to perform inference on this object. And so something that's very common in the fMRI literature is to use what's called cluster of inference. So let's say that we retain the cluster on the right here in red. So the idea of cluster of inference is to look at the size of the cluster to extract it. So here we have a cluster of 877 voxels. And you will compare this size to the size of a certain null distribution that you have at your disposal, which is basically telling you what the largest cluster size should be under the global null hypothesis, meaning if there is no single atom in the brain. And so if the size of the cluster to extracted is above so this size given to you by this null distribution, you will declare that the cluster is active. So this is sort of a binary decision. Okay. So the problem with this type of inference is that actually when you think about it in terms of statistical guarantees, which is what we are trying to do here, you are actually really not saying much, in the sense that the guarantee that you're getting is that there is at least one voxel that is truly active in your cluster with high probability. But of course, when you're dealing with clusters that are that comprise a few hundreds of voxels or even thousands of voxels in modern MRI images, of course, you're really not saying much with regards to the extent of the signal within the cluster. So this is a problem, actually. And another way of formulating the same question is to look at the TDP, which is the true proportion of active voxels in cluster. A more informative answer to this question. Okay. So the problem that you're going to run into to try to formulate a TDP or on clusters is a problem of selective inference, in the sense that you're using the same data for selection, meaning to form your cluster, but also for inference, meaning formulating the TDP lower bound. And this can lead to huge biases in the inference that you're actually making, in terms more precise in terms of false positive. And so this is something that is well known in the community, but I still want to emphasize it on a really trivial example, which is the following. So here you have a map in 2D on which we have generated null data, in the sense that this is null. There is nothing to find. There is totally no signal. Okay. And so what we're going to do is to perform the Benjamin-Hogburn procedure, which is the most standard approach when you're trying to deal with a multiple testing problem in this context. And so if you apply the Benjamin-Hogburn procedure to the whole map, so again, it's noise, you get no rejections, which is great. This is what you expect. And of course, you get an FDP of 0% because you have not rejected anything. So you make 0 false discoveries. So false discovery proportion is 0%. But now, if before performing the Benjamin-Hogburn procedure, you perform a selection step, which consists simply in thresholding the image, which is exactly what we've done before on our brain images when we found clusters. Right? So here we will say the 10% of the image that corresponds to 10% of smallest p-value. And if you perform Benjamin-Hogburn on this subset, you get 62% of these p-values that are rejected, so that are declared active. And of course, you get an FDP of 100% because since there is nothing to find, every detection is a false positive. So this is why you have 100% false positive. So you see that you're taking enormous risks on this subset for no reason, since there is nothing to find, but simply because you basically perform the selection step that is dependent on the data, and you have not taken this into account. So this is really the problem that we are trying to tackle. Okay. And so the thing that you want to do to avoid this problem is to have what we call false discovery proportion control, FDP control in short. In the sense that whatever the subset of hypotheses that you choose, so in practice, this will be a region of the brain. So here you have two sets in blue. You are able to control the proportion of false discoveries, which is the number of false discoveries, which are the red dots here. So you want a function V, which bounds, upper bounds, this number here, which is the number of false positives in S1. You want it bounded by V of S1, etc. And crucially, you want this to hold for all possible regions S, which means that you can select regions that are derived from the data. And you want this to hold with a high probability, so at least 1 %. And of course, this is equivalent to controlling the proportion of false discoveries, since you just have to divide by the kernel of S in the equation at the bottom of the slide, and you obtain the FDP, which is bounded by V of S divided by its kernel. Okay. So now moving on to the core thing, the core object we're looking at, which is what we call post-hoc bounds. So these are such functions G that will give you an upper bound on the number of false discoveries that you make in a given subset or in a given brain region. So actually, this already exists. I mean, the history of these bounds go way back in the stats literature. The first time that this type of object has been used for brain mapping is 2018 paper in neuroimaging, which is called RE, which stands for All-Resolutions Inference. And so you have the expression of the bound here, which may look perhaps a bit complicated, but the only thing that you should retain from this expression is the fact that you're comparing p-values, so py of x, p-values of your data, to certain threshold families, so alpha k over n here. And so there you get a post-hoc bound, right? And so what you can do with this type of bound is now, if we go back to our working example with the cluster that we extracted, instead of simply taking a binary decision in the way of using the cluster over inference, so declaring that either this cluster is active or not, we can formulate a lower bound. So here 40% using RE, meaning that we can guarantee with a high probability, 95%, that there is at least 40% of voxels that are active in this cluster. So this is a much more informative answer to the question that we are interested in. Okay. So this is what we are going to do. So that being said, so as I said, RE already exists in the first occurrence such an object in such a method, sorry, in my field. And so why can't we stop there? Because of course this is a valid bound. So I mentioned briefly the fact that you're comparing p-values to threshold families here. And so something that you can notice in this threshold family, so alpha k over n, is that this is fixed. So M is the number of voxels, and alpha is the risk level that you're going to tolerate. But this does not depend on the data characteristics, basically. So if you have two data sets that have the same resolution, this threshold family will not change. And this actually leads to conservativeness. And so this is why we are trying to improve this bound. So there has been a first step in the way of improving this bound in 2020 by Blanchard et al., which instead of using this bound, which is completely parametric, uses a sort of semi-parametric bound in the sense that here you see that you still have a linear threshold family, so K over N. But this time, instead of using alpha, you have a certain lambda that can be chosen using randomization on your fMRI data. So I won't get into the details, but the idea is that you can be less conservative by tuning this lambda parameter and still having a valid bound. And so this is called semi-parametric bound. And so Notip, which is what I'm presenting to you today in the context of the course, is so a method that we've developed with Alexandre, which is fully non-parametric. So the idea is that instead of having to fix shape of threshold family, so here linear threshold family as in RE or as in Blanchard et al. 2020, the idea is that we learn TK directly from the data. So this TK is can be potentially non-linear. It can be basically of whatever complicated shape. But this yields, so we construct TK in a way that this yields a valid bound, which is less conservative than the two bounds that I discussed previously. And so this is what I want to show you now, a really concrete example. So this is the type of inference that we are looking at when trying to compare these methods. So here we're taking some data from Neurovault, so an fMRI data set. And so what we are doing with this data set is that we are trying to find the largest possible region using the two methods at hand here, so RE and Notip, which controls the FDP at a level of 10%. So the largest possible region for which can guarantee that the FDP that there are less than 10% of false positives in the region. And so we do that both with RE and Notip. And so we print here the regions using Nylon and Python that are detected. And so here you see with RE that you have detected 2,000 voxels approximately, while with Notip you detected over 6,000 voxels, which is a huge gain in detection power on this data set. And so to show you that this is not simply cherry-picked on a given data set, we conducted extensive experiments on 36 fMRI data sets taken from Neurovault again. And so we've considered the methods in various settings where we are requesting different FDP levels across 36 different data sets. And what you see, especially in the grouped box plot in the middle, is that on average, Notip, so using a fully non-parametric procedure, will yield a region that is 40% bigger than the one that you would get using RE, which is a fully parametric method. So this is the experimental study that we conducted to show the interest of non-parametric procedure in this context. So that being said, we've also evaluated the robustness of the procedure with regards to low sample sizes. So we've considered, again, additional fMRI data sets. So each point is an fMRI data set, which contains at least 8 subjects and up to 200 subjects. So we're looking at the variation of the size of the region that I just explained. And so you see that there is more variability, of course, when you are dealing with low sample sizes. And you see that there can be some sort of catastrophic behavior when you're dealing with extremely small data sets. So here we have around 15 subjects on this spread plot. And so basically the take-home message of this robustness study is that we should avoid using, basically performing inference on data sets that are extremely small, so extremely low sample sizes. So because instability can occur with every method, including ours, including Notip. And so something that we experimental study that we performed is looking at simulated data that mimic the dependent structure of fMRI data. So basically, this is a sort of sanity check where we control everything, and we can look at basically the proportion of false discoveries that we make on the regions that we detect with this method. So what you see here, so the important part is the one on the far right, which is so here we are plotting the false discovery proportion of the three methods at hand. And so what you see here is that the false discovery proportion is indeed controlled with Notip. So you have 1,000 simulations here, and in only 5 or 6 of them, you exceed the required FDP, which is 10%. So you are well inside the margin that you have, which is 50 simulations, since you are taking alpha close to 0.05. So you see that FDP control is indeed preserved on simulated data. And this is important to evaluate because, of course, on real data, since you do not know, you don't have access to the ground truth, you cannot evaluate FDP control. And also, we've looked at power in the case of simulated data, and you see again that the Notip again exhibits substantially superior power compared to the two other methods at hand. So RE, so Neuroimaging in 2018 and Blanchard et al. In 2020. And so notably, you can look at the box plot in the middle, again on 1,000 simulations, the same as in the previous slide. And you see that on average, the region that you will find using Notip is twice as big as the one that you would find using RE. So again, this is, well, this confirms the message that we are trying to convey, which is the benefit of using a fully non-parametric approach in this context when doing inference with fMRI data. Okay, and so I'm left with a few minutes to conclude so this part of the educational course on Notip, which will be also followed this afternoon by the tutorial session during which we'll use the code, the Notip code base, which is publicly available in Python in the bottom of the slide. And so what we've seen in this theoretical talk is that is basically the relevance of the multiple testing tools in brain mapping, and also the need for post-hoc bounds because of these problems of selective inference. And so regarding the main contribution that I've shown to you today, which is the idea of learning the TK, so the threshold family, to gain power, we've seen that it yields around a 40% increase in power compared to RE on average across many different data sets. And also another important message is to avoid using Notip, or for that matter, any other method of the kind, on extremely low sample sizes, because instability may occur and one may get catastrophic behavior. And so what I've shown here is simply on the one sample and two sample designs. And so an idea, possible extension could be to go further in basically the general linear model. So you have a preprint by Samuel Davenport, which is also a speaker today in the course on archive. And so again, I want to stress that everything that I've shown today is fully reproducible using the Notip repository, which is on the slide. So it's Python code we'll use in the tutorial as well. And you can find details about technical stuff, about math, and also about additional experiments on the fMRI data in so Neuroimaging paper in 2022. If you are interested. So thanks for your attention, and have a nice day.